Exactly. Thank you. I can assure you that I'm not dead. Alas. Right, so yeah, I wanted to carry on with where I was, and as I mentioned the other day, I'm sort of slightly editing the order of things, and so what I'll do today is I'll continue talking about algebraically maximal Kaplansky fields. I just introduced some of these definitions yesterday. I'll talk a little bit, just very briefly, a little bit about what happens if you drop the assumption that the field is perfect. You weaken the definition a little bit, suitably. And then I'll talk about tame valued fields. Actually, but between the two things, I might talk a little bit about the case of unramified valued fields and mixed characteristic. Then I'll outline the theory of tame valued fields and separably tame valued fields. And then if there's time, which I really hope there is, I'll say a word about recent applications of that theory to the theory of perfectoid fields, the model theory of perfectoid fields. Let me just draw my picture again from yesterday, which is the following. What we're generally doing in these embedding lemmas is taking a valued field, which might have been algebraically closed in my first type of example, or henselian equal characteristic 0. We take some kind of section of the residue map, I look at the image, I see the image as a subfield. This is the plan of campaign in equal characteristic, right? This doesn't make sense exactly in mixed characteristic. I can also look at cross-sections of the valuation, which are functions, which are group homomorphisms from the value group into the multiplicative group. Maybe call that something like T to the gamma. Right, we can then see these as somehow suitably disjoint, and therefore we may look at their kind of now meaningful amalgam. We can look at the compositum, and it sort of can only mean one thing. Then I want to think about the relative algebraic closure of that compositum in my field K, relative algebraic closure. And so the embedding problem tends to break down into understanding this extension, or at least this whole extension, but paying close attention to what's going on here, and to this extension, trying to understand what's going on here. The key point being that this is always immediate, this is immediate as well, but it's algebraic. This is immediate and relatively algebraically close, or regular, maybe we should say, regular extension. Okay, so this is the same pattern of argument that we'll see in the algebraically maximal Kaplansky world. So let me pick up those definitions. So K was Kaplansky, satisfies Kaplansky's hypothesis A, is another way of putting it, if either the residue characteristic is 0, that's supposed to be the boring case, or the case covered by existing theory, or it's a residue characteristic P positive, and the value group is P divisible, the residue field is perfect, and the residue field does not admit, or there doesn't exist, does not admit proper Galois extensions of degree divisible by P. Okay, so in particular, no Artin Schreier extensions, something like that, but that's a bit weaker than saying that. So this is what's the point of this definition? Where does it come from? This comes from Kaplansky's analysis of those limiting values of polynomials that we talked about the other day, limits and possible limits of v(f) of A, as A, in a suitable sense, tends to some element x in a field extension, in an extension of K. And in particular, Kaplansky's theory says all polynomials have somehow attain a limit value in some neighborhood of x whenever x is an element that generates a simple immediate extension of K subject to these hypotheses. Right? So if K satisfies these hypotheses, then you're not going to get any polynomials that somehow behave badly, that do not get the correct value in some sense as you get suitably close to x within K. So under this hypothesis, K already in some neighborhood of this element x, which lives outside of it, already sees a stable value for every polynomial. And so in that sense, the isomorphism type in the language of valued fields of this simple extension is somehow determined by that behavior, by those limiting values. Because there's no choice. V of f of x must take that limiting value. And there's another consequence, which is that Kaplansky, as a hypothesis, tells us that K has a unique maximal immediate extension up to isomorphism over K. Up to isomorphism over K as a valued field, there's a unique maximal immediate extension, and just as well I could say unique maximal algebraic immediate extension over K. So what has that got to do with anything? Remember I said the role of this extension in these structural arguments is that this thing, which is as it were the subfield of K built from the residue field built from the value group, has this little bit of algebraic extension above it. And that has to be immediate. There's nothing left to do. There's no ramification to witness here. There's nothing happening in the residue field because that's all already appearing here. So this bit is just immediate, and it's hard, we can't really control it by the value group and residue field, of course, by its nature, unless somehow automatically its structure is determined, unless it's got this up to isomorphism fixed behavior. So in this Kaplanskian case, this extension is sort of well determined enough that if we can embed this into some other value field, then we can embed that. Assuming that the codomain is supposed to be itself closed under immediate extensions or closed under algebraic immediate extensions. So with this hypothesis, the Kaplanskian hypothesis, plus assuming that it is algebraically maximal itself, i.e. admits no proper algebraic immediate extension, right? We've now, when we put these things together, we get what I would call AMK, and you can think of that as a class of valued fields, but it is also an L-val elementary theory. There's some axioms that you can think about writing. You can think about what it means to write down the axioms for algebraically maximal Kaplansky. That's entirely non-obvious, but it is there in the literature. So there is an L-val axiomatization of this class, and we do get embedding lemmas just as I wrote down yesterday for the class of Henselian valued fields of equal characteristic 0. Also for this class we get suitable embedding lemmas. Before I write anything down like that or give any kind of consequences of that, let me just briefly outline a slightly more general collection, which is to say separably algebraically maximal Kaplansky. Just means Kaplansky, and separably algebraically maximal, which admits no proper separable algebraic immediate extension. It's a bit of a mouthful. Why is that interesting? Or why would we imagine that restricting our hypothesis to only separable extensions would be a good idea? Well, the point is, valuations always prolong uniquely to a purely inseparable extension. So the idea is, if you can take care of separable algebraic extensions, you should be able to take care of the purely inseparable bits that remain. Up to isomorphism, they're going to already be fixed. That's the idea. And that's also L-val axiomatizable. I don't want to stress you out too much with thinking about these things. Best to just start focusing on the algebraically maximal Kaplansky things if you've not seen this before. Okay, so we have the usual embedding lemma. I won't write it down, so I'll omit that, because it's essentially the same as in the Henselian equal characteristic 0 case. And we get the usual corollary, which is a theorem, which could be variously attributed to many people, but maybe I'll say Delon as the kind of first reference there, which is that algebraically maximal Kaplansky valued fields form an AKE class for these for this collection of binary relations between structures. So if you have two algebraically maximal Kaplansky fields, supposing their characteristics line up, I should say taking care of characteristic, that's the field, right? Be it in mixed characteristic or equal characteristic, P or 0, and suppose that you've got residue fields elementarily equivalent and value groups elementarily equivalent, then, because the other direction's much more trivial, the value fields themselves are elementarily equivalent. So that's for two models. And I should put here that the characteristic of K should equal the characteristic of L. Otherwise, I might end up claiming that a characteristic 0 field is believes that 2 equals 0. All right. So, great. So far, so what? Well, just as a remark, from a model theory point of view, this is quite an interesting class of fields, because, as it turns out, from a model theoretic point of view, there's this model theoretic property called not the independence property. And in characteristic P, not the independence property implies separably algebraically maximal. So we, therefore, if only we had, characteristic P, NIP plus Henselian implies separably algebraically maximal Kuhlmann. There's a lot of work going into that. I won't try and attribute it all. So this means that we get an AKE-theory based on what is really an abstract combinatorial property of valued fields, the definable sets of valued fields. So that's one kind of point. So what about these standard conclusions then? Well, we get the usual standard conclusions around decidability transfer. E.g., and I'll just give an example statement, if K is an algebraically maximal Kuhlmann field, then the L-val theory of K is decidable if and only if the theory of its value group and residue field are decidable, which I could write like, I could write that in various ways, but let me just make the slightly stronger statement that they're at least Turing equivalent. Okay. So if you can decide these two theories, then you can certainly decide this theory, as an example. Let me give another corollary of this, really of the embedding lemmas rather than of the AKE principles themselves. And this is due to Halevi and Hasson in the case of algebraically maximal Kuhlmann fields, and due to Soto Moreno in the separably algebraically maximal Kuhlmann case. I'll state the A and K case first. So this theory, algebraically maximal Kuhlmann plus equal characteristic, so for example, equal characteristic P, that's what I'm really talking about here. This theory has quantifier elimination relative to the value group and residue field sorts. In what language? Well, in the language with the angular component that we talked about yesterday. So you get the same behavior as in Henselian valued fields of equal characteristic 0 when it comes to definable sets. That's my claim anyway. Okay? This is a definability conclusion. This gives you some way of discussing the complexity of definable sets. Let me just write down the imperfect version of this. Separably algebraically maximal Kuhlmann, an equicharacteristic, which is the only case that differs from this one anyway, has QE relative to these sorts in a language LAC plus what are called the parameterized lambda functions. What are they? If you don't like inseparable fields, you better just close your eyes for a second. The parameterized lambda functions, these are essentially pth roots of the coordinate functions of a field, let's just call it K, as KP vector space, the subfield of P powers, with respect to bases or independent sets which themselves appear as parameters. So without, they're appearing parametrically. So your function takes an element and a sort of potential basis, and then it returns the various returns the various coordinates, or in fact their pth roots, of that element with respect to that basis. It sort of takes into account all bases at the same time. So it doesn't pick out a basis. That's what a parameterized lambda function is, and this is basically a standard tool in the model theory of imperfect fields, which allows you to get over imperfection. So, just as an example, if I can call this language LAC lambda, then you'll... In fact, it's a special case of this, but it was known a long time in advance. But let me just write the name Hong as an attribution. The theory of separably closed valued fields admits QE, full QE, in the language of rings with the lambda functions, the parameterized lambda functions. Okay. Did I say rings? I mean valued fields. Okay. That's an aside. I don't want to get into this imperfect world too much. Okay. There are alternative approaches are available. I should say that a range of authors like Basarab, Kuhlmann, Belair, Flenner, and many others have obtained QEs in different kinds of languages, be it taking different quotients of the multiplicative group, for example, using the map that goes from k times to k times mod 1 over the maximal ideal, which is called an RV structure. QEs exist in this kind of language too, but I don't have time to give all the different possibilities. Okay, so one fun little corollary of all of this is perhaps let K V be an algebraically maximal Kaplanski field of equal characteristic. Then maybe, and let's take A being K transcendental over a let's say a sub-value field C, some sort of constant subfield, then any C definable set containing A has non-empty interior. And that's because essentially all we know about A is that it's transcendental and maybe that its residue is that thing. And the residue of every polynomial rational function of it is, that thing and that thing. And I'm allowed to fix those things, and any finitely many of them I fix, I'll still stay in a nice open ball around A. Everything in a certain little ball around A is going to have the same quantifier free type, even fixing all the residue and value group elements. Okay. Note that this is absolutely not true in the separably algebraically maximal Kaplansky world, if I'm really in an imperfect example, because you can get all sorts of nasty behaviours with inseparable extensions. I won't get into that. Standard conclusions, computable eliminations. Yeah, and as a kind of, what's really going on here is of course we get this, computable elimination. Which is going from formulas in the language of valued fields to Boolean combinations of quantifier-free formulas in the language of valued fields, plus formulas from the language of the value group, the language of the residue field. Now here I'm just lying a little bit, because what I mean, if you're already a model theorist, this will make perfect sense to you. If not, I'll give an example in a second. Of course, what I mean really here is you take some formula that has variables that may include variables from capital K. We're going to be able to rewrite that up to equivalence in this theory as some sort of combination of quantifier-free things of the same sort, plus something like my value satisfies this formula coming from the value group. My residue satisfies some formula coming from the residue field. So we have to take formulas phi composed with a term, suitable term, that maps variables in the main field sort into the value group sort. For example, one needs to be a bit careful about that kind of thing. But that's essentially what this quantifier elimination is about, this kind of elimination. And just as in the case of henselian valued fields of equal characteristic 0, we get, but now it's, now I want to state it like this, now we get This is just a kind of quantifier elimination statement, which is both about the complexity from a computability theoretic sense, because I'm telling you it's a computable elimination, and about the complexity of definable sets. Okay, let's see. Let me now change topic. So I want to talk about a different family of AKE principles. So this is the finitely ramified world. And just to be clear, I'm talking about mixed characteristics. So I think Blair's already mentioned the model theory of QP yesterday. And what was that? The theory of QP as a valued field is basically described by saying I'm a valued field of mixed characteristics. I'm a valued field of mixed characteristic 0p. My value group looks like Z. I need to be a little bit more careful there. I have to pick out that P gets given the minimum positive value, and that my residue field looks like, models the theory of FP, where, of course, finite structures are kind of boring from our point of view, so I could just write isomorphic here. Missed out one axiom. What's that?
Characteristic?
No, I said about the characteristic, but I also need to say henselian. Okay. All right. So Blair's already told us that this was the theory of QP, and this is also part of the AKE story from 1965. How do they do that? What's the kind of short and sweet proof? Well, the short and sweet proof is the following. Let KV be a model of this theory. Can I call it T just temporarily? The point is I don't know yet that T is really this theory. So just take some sort of model. Standard model theoretic trickery, I'm now allowed to blow up KX. KV. That means take what I was calling an elementary extension, or if you like, an ultra power. Right? So we're allowed to make it bigger while keeping the same theory. So without loss of generality, KV is suitably big. More precisely, suitably rich. Even more precisely, any descending chain of non-empty definable sets, let's just say an omega index chain, any descending omega index chain of definable sets, each of which is non-empty, is non-empty. That's a kind of compactness property, isn't it? That's exactly the magic of going to these elementary extensions, that we get this kind of behavior where you get these limit points. Modern theoretic terms, this is called realizing a type. Second conceptual link is to think about, which I already mentioned, and Blair's already mentioned, the concept of a coarsening.
Do you mean that its intersection is non-empty, or?
Yes, thank you. Has non-empty intersection. There we go.
It's like, but I can always take the empty.
Oh, you're quite right, thank you. Someone's listening. Much appreciated. Okay, so what's this business about coarsenings? Well, coarsenings, I describe them as allowing yourself to go to a bigger and bigger valuation room within the same field. Perhaps a slightly more useful for our purposes way of thinking about it is that it's about quotienting the value group by larger and larger convex subgroups, literally sort of coarsening the function. So if instead of considering the main valuation here, V, I instead consider its friend, like that, I get a coarser valuation. Now hang on, what's this Z here? Well, that's really Z times the minimum positive element. There was a sort of minimum positive element here in this gamma. So that should really be the value of P. So it's the convex subgroup generated by the value of P, which also coincides with the smallest non-trivial convex subgroup. Right? So this valuation, let's call it V plus, what kind of valuation is that? Well, I can tell you a couple of things. K with V plus is Henselian. It's of equal characteristic P, where P is 0. So I should have said 0. Okay? Equal characteristic 0. Now, why is that? Let's think about where P goes in this story. The P goes here to the smallest positive element of gamma, which in this group is 0. So P goes to 0, which means P is not in the maximal ideal, which means P does not go to 0 in the residue field. So P is not 0 in the residue field. That's why we're in equal characteristic 0. Also, this group happens to be divisible. I think you can probably believe that. That's a bit like, check that for yourself.
Why is it not 0?
This group? That's a really good point. So here's one chain of here's a chain of non-empty definable sets in the group. Maybe I should. No, that's fine. I'm happy with that. Yeah. Okay. So that's fine. There is something out there. There is something beyond, extraterrestrial. So this tells us that our already existing theory of equal characteristic zero Henselian valued fields applies. Okay, this is great. I'm very happy now because our already existing theory of equal characteristic zero Henselian valued fields tells us what? It tells us that we can understand this valued field KV plus just in terms of being Henselian and having a divisible value group and a certain residue field. So if only I can find out what that residue field is, then we're good to go. Any ideas what that residue field is? Any ideas? So tell me, suppose I had this property true in Q star. Suppose every omega chain, descending chain of non-empty definable sets in Q star had some point in it. And then I took the residue field of this coarsening. Okay, it's not a coarsening now because I'm doing something with an order. But remember my example with Q star, right? This here is the convex hull of Q. I suggested that you went away and worked out what this thing, let's call it O because it happens to be a valuation ring, what O mod M is, and the answer was it was a real closed field. And so now what I've got is K, some big thing K, and I've now got, if you like, K started from a copy of QP, if you like, and then I blew it up so much so that this I don't know, I want to sort of try and draw a picture of the field as though it's stretched out along the value group. What I'm doing now is I want to see it as an equal characteristic zero valued field, where this is now this and the equivalent thing in the sort of minus natural numbers. That's your zero in the quotient group gamma mod z. And then I want to say, what's the residue field, right? What's the residue field of this thing with respect to this valuation ring? Well, it's got to be a kind of saturated, a filled in, an elementary extension version of whatever it was I started with. In the same way that this thing is a kind of saturated, filled in the holes version of Q. So what we actually get is, to spoil the punchline, is that KV is already, in fact, isomorphic to UP itself. Because I filled in all the holes. Every element of QP is, after all, the limit of a countable sequence. So I just think of that countable sequence of elements. I describe definable sets around them converging closer and closer. These things describe a Cauchy sequence. I've now got some element out there, possibly differing from an actual element of QP in some sort of infinitesimal way. And then what I've done is I've exactly taken the quotient, which then kills off the difference. So the residue field here is QP itself. In the same way that the residue field here, if I assume that Q star really had that filling in all the holes property, it really would be R. So that tells us now we now know the following. By Kochen-Ershov principle in equal characteristic 0, we now know that K with this valuation has the same theory as QP with the T added value. Okay. Now, in fact, that's also true for the QP. I mean, I could have, certainly QP itself is a model of this theory T, this sort of, I'm trying to axiomatize the theory of QP thing itself. So what I've really showed here is that any model is elementary equivalent to a model of this type. And so I've sort of showed T is complete. Right? All models are elementarily equivalent. Now I've just lied to you in a little way, which is, of course, here I'm talking about this valuation, not the original one. But thankfully, Blair's already told us that Julia Robinson's formula allows us to note that this valuation V, or rather its valuation ring, but also its maximal ideal, so really everything about the valuation, is L ring definable, even without any parameters. So it's very, very nicely definable. So that's what enables us to recover an elementary equivalence between any two models of T as valued fields in their correct language, in the correct sense, with respect to the correct valuation. So that means T is complete. So it is the theory of QP as a valued field. Okay, that's another classic Kochen-Ershov theorem, also from that string of very great papers. Let me now tell you the kind of general view of this that we now have. I'll now sticking to, just for the sake of time, I'll stick to the unramified setting, which means that VP will always be minimum positive. We get a general theorem, which is let KV be unramified Henselian. And of course, I'm meaning mixed characteristics. Right? For the purpose of today, unramified just means mixed characteristics. And this. Unramified Henselian. Then the theory of KV, comma V, is axiomatized by some analogous theory to this one here, this T. Now I just need to now write out what that analogon is. So it's a strictly more general problem. So I have to say, I am a piece of chalk. I am Henselian, valued field, mixed characteristic, right? Okay, the basic background theory, if you like. I have to say my value group, and I should distinguish them this particular element to make sure that I don't accidentally forget to axiomatize the unramified part, is elementarily equivalent to this thing with its minimum positive element. I've got into a pickle because it looks like I'm writing the same symbol twice, but this is supposed to mean in any model we insist that its minimum element, maybe I should call that 1. 1, but here I mean the minimum positive element in gamma, satisfies the same theory as whatever it was we started with. Now it doesn't have to be Z, right? Because I didn't specify that this thing had a rank 1 value group, right? We talked about, both in my other talks and in Blair's talk and in Francis' talks, we've talked about valued fields of higher rank. So it doesn't have to be Z. It's something that has a bit of Z in the middle, a little bit of a convex subgroup Z, but it doesn't have to actually be Z itself. Nor does it have to be Z with something divisible once you quotient by Z. It could be something a bit more complicated than that. It could be Z lexicographic product Z, for example. And I need to say what that residue field is. So I need to say that my residue field of my model is elementarily equivalent to the residue field of the model we started with. And you know, that's enough. That's actually enough to axiomatize the theory.
Unramified?
Sorry, say again.
Unramified.
Mm-hmm.
What does it mean?
Generally what I'm trying to say is that the value of P, the residue characteristic P, is the minimum positive element in the value group. And I'm also therefore including the assumption that we're in mixed characteristic 0P. So it's something like, I mean, if you prefer thinking about number fields or finite extensions of QP, it's something like an unramified extension of QP, for example, if you prefer thinking about that world. Okay, now that's a theorem, but the underlying kind of thing that I'm really telling you is, i.e., for unramified Henselian, we have, or satisfy, or whatever, we have AKE in all suitable symbols. That's a little stronger than what we've written here. What we've written here is about the elementary equivalence symbol. Suitable AKE principle, relative to the background theory. Relative to the background theory. And again, we get a computable elimination on the level of sentences. Right, so each sentence in the language of valued fields gets translated, gets eliminated into a sentence that's about value groups, combined Boolean combination, residue fields, in order that in any model it is true that the original sentence is true if and only if that eliminated more simple version is true in the value group in the residue field. And that association is a computable one. But I'm not claiming that there's a straightforward quantifier elimination here. There are various quantifier eliminations, which I don't have time to get into, but a bit more complicated. Let me make a remark, which is I need to tell you how this proof goes a little bit. Now it's the same, proof is the same as for EP, but I should take care of one extra thing. Because this argument here, right, I said here that the residue field was QP. Well, the residue field isn't going to be QP anymore. It's got to be some other canonical object there, playing the role of a complete, discrete, unramified valuation ring. Thankfully, there's obviously a very, very solid theory of such things. But for CDVRs and their structure theory, also their relative structure theory, how they relate to each other, in place of the above argument. Or really, you could say this is an example of that. Or really, this was an argument that whatever this KV plus was, it should be complete and discrete. And then I just said, well, listen, it's a complete discrete thing, and with respect to its valuation, it's therefore got to be the field of fractions of width vectors of FP, which is QP. And there's a little subtlety which one must allow, in the generality I've stated, it must allow imperfect residue fields where the width vector theory doesn't work exactly, but it doesn't affect the conclusion. Okay. That's a sort of longish story, but what the conclusion I'm trying to give you is that we do get a nice AKE theory. We do get a nice theory of Anscombe and Ershov theorems. Another remark. There is so in the finitely ramified world, where I allow VP to not be the minimum positive element of our value group, but to be, you know, the 17th positive element, some finite number. We also get a range of Anscombe and Ershov principles, but I have to write the word suitable in, which is my favourite weasel word, because you have to make some adaptations. Suitable AKE principles to allow a little extra structure on the residue field, which essentially accounts for the ramification. You just have to be able to describe that extra bit of ramification. And I'm going to not go into that now. I've only got a few more minutes left. I'm way out of time. So let me just indicate the final context of AKE principles that I want to talk about today. Which is for the theory of tame value fields. So the theory of tame valued fields is a theory introduced by Franz Victor Kuhlmann, which generalizes the setting of algebraically maximal Kaplansky valued fields. How do you generalize that? Well, essentially, instead of forbidding all Galois extensions of degree divisible by p, instead one simply forbids defect extensions. So extensions where the fundamental inequality this fundamental equality fails to, where one has this extra p to the d appearing non-trivially in the fundamental inequality. I forgot to do the squeegee bit, didn't I? The most important bit. Okay, so what are tame valued fields and what's their AKE theory? Thankfully, the story is remarkably, or rather, at least the statements are remarkably clean. So I should say, I do think it's really important to notice that although the context of tame valued fields is significantly more general than the algebraically maximal Kaplansky setting, the results are essentially as good, almost as good. So tame value. Definition. KV is tame if it's defectless, henselian, so we have this equality for every finite extension. Right? There's no defect appearing, there's no p to the power of d appearing on this right-hand side. The residue field is perfect, and the value group is p divisible. And I should say, I mean here, the residue characteristic is p. If p is 0, then we're not saying anything, or just replace p by 1. So this is the setting of tame valued fields. It is L-val axiomatizable. There is a theory of tame valued fields. And we do get an AKE theory along the following lines. Kochen theorem due to Franz Victor. If I have a moment at the end, I might throw in a few more comments about the way this gets generalized. I don't think I do have time, so I won't. The class of tame value fields is an AKE class for now that looks significantly weaker than what we knew before. This statement on its own is a lot weaker. We lose the absolute statements that tame value fields satisfy an AKE elementary equivalence principle. They do not, in fact. It's known. But that's because of problems that appear in mixed characteristic. In tame valued fields of equal characteristic are also form an AKE class for the other two symbols. So somehow it's all to do with finding different valued fields in mixed characteristic where you don't get a nice common substructure over which to do the various embedding arguments. That's what it all comes from. So in fact, these statements are indeed false in mixed characteristic. But this is the general theory, and just one word about the proof, and I think I'm out of time. Proof idea, it's the same basic structure as for the other AKE principles. We have step one, if you like, which is a structural argument. Let's just say that we're an equal characteristic, since I'm only giving you the briefest of subfields. Now, our hope would be to take a section and a cross-section, play the same game, hopefully get a unique algebraically maximal extension here, blah, blah, blah. Let's say relative algebraic closure, and then hope to carry on like that. Now, this doesn't work in this setting. It doesn't work essentially because this extension is very badly behaved. Right? If you just naively take a section and a cross-section, amalgamate them, there will be some nasty defect in generality appearing here. And there's a great example of that. Look, for example, in FP double brackets T to the Z, but where I've allowed division through by P. In this valued field, I definitely get some nasty behavior happening in here. But so what's step two? Step two is to play this game, work instead at the level of function fields. Because if instead of trying to embed all of K at once, where you get this problem, instead what you work with are function fields living inside K over F, and for such function fields, K0 over F, everything works out much more nicely. In fact, the picture then divides nicely into this two-step part, where you really do now get a nice subfield which admits an embedding from the residue field, value group. You get something trivial happening here. You get then a nice extension here over which everything else is now well behaved by Kaplansky theory. We're in that case where all polynomials get limiting value in some neighborhood, and somehow, moreover, you can understand this extension, which may have, you know, a large transcendence degree, you may understand it one transcendental element at a time. And the two ingredients here are, to understand this portion of the argument, one uses the generalized stability theorem, and to understand this portion of the argument, one uses Henselian rationality. But my message to you is that this exactly refines the kind of argument that one does in Henselian equal characteristic zero, algebraically maximal Kaplansky fields, and so on. It's the same broad structure, but with these much more powerful tools used to deal with getting rid of nasty behavior here. And the main simplification is to work at the level of function fields. And then by model theoretic magic, if you can embed an arbitrary function field inside your K into some other L, then you're good to go. There's a lot more to say, but I'm out of time.